Hi everyone, this video we are going to go over some related rates problems. For new calculus students this may seem daunting, but it's really not that bad. We will go through some common examples. They include the falling ladder problem, volume problem, and a hot air balloon problem. We begin with a classic calculus related rates problem, the falling ladder. This is something every calculus student has seen at least once, and the problem goes as follows. A ladder 25 feet long is leaning against the wall of a house. The base of the ladder is pulled away at a rate of 2 feet per second. How fast is the top of the ladder moving down the wall when the base is 7 feet, 15 feet, and 24 feet from the wall? Looking at the problem, we can model the situation with the ladder acting as the hypotenuse of a right triangle. Its height will be sliding down, and base will be extending forward. Here we can see the extremes of the problem. So our first step here is to translate this word problem into mathematical expressions. We have c is equal to 25, which we can rewrite that as c is equal to 25 again to keep track of it. Its base is being pulled away at 2 feet per second, so we need to rewrite this in the language of derivatives, dB dt. And we can write dB dt is equal to 2 feet per second, remembering our units. And let's correct c to equal 25 feet. Our goal is to find the rate at the top of the ladder, which we can relate this as dA dt, and this is what we're trying to find. Now we need to find this when b is equal to 7 feet, when b is equal to 15 feet, and when b is equal to 24 feet. Because we're working the lengths of a right triangle, we should apply the Pythagorean theorem, which is a squared plus b squared is equal to c squared. We should take note here that c squared, which refers to the length of the ladder, is a constant. The ladder rate cannot change. Because we're doing calculus, we should take the derivative in order to find the related rates. So we differentiate the Pythagorean theorem in order to get 2a dA dt plus 2b dB dt is all equal to 0. So now we want to find the side length a, which we can do this by applying the Pythagorean theorem. So drawing a right triangle, we have here in our problem statement that b is equal to 7, c is equal to 25, and now we just need to find the missing side length a by applying the Pythagorean theorem to solve for it. Solving the equation for a, we get the missing side length as a is equal to 24. Our last step here is to use the differentiated form of the Pythagorean theorem that we got above to solve for dA dt. Isolating dA dt, we get negative 28 over 48, which we can simplify this down as negative 7 over 12, and remember our units, feet per second. Next up, we gotta solve it when b is equal to 15. So if we apply the Pythagorean theorem once again, we can solve for the missing side length a. We get a is equal to 20. So now our job is to plug this into differentiate Pythagorean theorem just like before in order to solve for dA dt. So we know a is equal to 20, we're trying to solve for dA dt. We know that b is equal to 15 and that dB dt is equal to 2. So now we just gotta isolate for dA dt. Doing the algebra, we get that dA dt is equal to negative 60 over 40. Which we can rewrite this as negative 3 over 2, and remember units, feet per second. Next, we have the case when b is equal to 24. So once again, to solve for a, we need to apply the Pythagorean theorem. Solving this through, we get a is equal to 7. And just like before, we plug this into implicitly differentiated Pythagorean theorem. So now we have our values. A is equal to 7. We leave dA dt by itself. b is equal to 24, and dB dt is equal to 2. So solving for dA dt, we get this as negative 96 over 14, which we can simplify it down as negative 48 over 7 feet per second. Next up, we're going to do another related rates problem, this time regarding volume. Next up, we have a volume of a sphere problem. So air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. Our job here is to find the rate of change of the radius when the radius is 2 feet. So let's work this through. We begin by noticing that the volume of a sphere is equal to 4 over 3 pi r cubed. The problem states that the rate of change of the volume is equal to 4.5 cubic feet per minute. Translate this as dv dt is equal to 4.5. It also states that the radius is 2 feet, so we rewrite this as r is equal to 2. Now we apply implicit differentiation to the volume formula to get dv dt is equal to 4 over 3 pi 3r squared dr dt. We cancel out the 3 to get this new simplified form of dv dt. From the problem, we have dv dt is equal to 4.5, so now we just substitute this in. We are looking for the rate of change in the radius, which is dr dt. So now we just need to isolate for dr dt. So this becomes 4.5 over 16 pi, and the unit here is feet per minute. Next up, we have a hot air balloon related rates problem. Alright, so here's a hot air balloon problem. The angle of elevation is the angle formed by a horizontal line and a line joining the observer's eye to an object above the horizontal line. A person 500 feet away from the launch point of a hot air balloon, and the hot air balloon is starting to come back down at a rate of 15 feet per second. At what rate is the angle of elevation theta changing when the hot air balloon is 200 feet above the ground? So our first step here is to draw a picture to get a better understanding of the problem. We see it is a right triangle with a base of 500 feet. The height is modeled by y. Our job here is to find d theta dt, and we are trying to find this when y is equal to 200 feet. Since the balloon is coming down at a rate of dy dt, we can model this as dy dt is equal to negative 15. The reason why it's negative is because we are going down, so be careful and make sure to remember our signs in related rates problems. Since we're working with angles, our best bet here is to use tan theta, which is opposite over adjacent. The opposite side is y, and the adjacent side is 500. Next up, we differentiate both sides. The derivative of tangent is secant squared theta, d theta dt. And for the right hand side, we have dy dt all over 500. Our goal here is to find d theta dt, so we're going to move everything to the right hand side in order to get d theta dt all by itself. What we're missing here is the angle theta, so here is how you should find the angle theta. We can observe here the adjacent side is 500 and the opposite side is 200, so we can write this as tan theta is equal to 200 over 500. We take the arctangent to get theta by itself, so theta is equal to arctangent 2 over 5. And when we punch this in a calculator, we get theta is equal to 0.38051 radians. Now that we have theta, we can get d theta dt. So we just plug in our values. Remember that dy dt is equal to negative 15. We divide that by 500. Now we plug in our theta value, which we got from above. Now we can put this entire expression into a calculator in order to get negative 0.02586 radians per second. So there we have it. We have 3 worked through examples. Here are some general guidelines for solving these problems. The first step is to draw a picture. A lot of math is really just drawing pictures. We should translate the words into mathematical expressions. When you see the word rate converted to derivative notation, the word at usually means plugging in that value. You should also keep track of what you're solving for. You should also understand the geometry of the problem, which means knowing volume formulas, the Pythagorean theorem, and etc. And remember to perform implicit differentiation and the chain rule. This is really important. Last but not least, remember units, especially in your final answer. So there you have it, but the most important thing here is to practice. And with that, I'll see you next time.